From succulent to synapse, aloe vera's hidden phytochemistry enters the Alzheimer's arena. The ancient desert plant has long soothed sunburns and skin ailments, but tucked within its gel-filled leaves may lie something far more surprising, a clue to fighting one of medicine's most stubborn foes. Aloe vera, or Aloe barbadensis Miller, is not, botanically speaking, a shy plant. A member of the Asphodelaceae family, it bristles with serrated, fleshy leaves and stores a remarkable pharmacopoeia of secondary metabolites within its parenchymal gel. Compounds evolved not for human medicine, but for the plant's own defense and survival in arid environments. Now, scientists are learning that this desert succulent's phytochemical repertoire may extend into territory no one expected. The fight against Alzheimer's disease. A new study published in Current Pharmaceutical Analysis has turned computational tools toward the leaf chemistry of aloe vera, finding that one of its naturally occurring plant sterols, beta-phytosterol, shows striking potential as a dual inhibitor of two enzymes central to Alzheimer's progression. A Phytosterol steps into the spotlight. Beta-phytosterol is no pharmaceutical novelty. It is, in fact, one of the most abundant plant sterols in the natural world, found across hundreds of species from saw palmetto to pumpkin seeds. In aloe vera, it is one of dozens of bioactive compounds tucked into the leaf's interior, sharing space with polysaccharides, anthraquinones, vitamins, and minerals. Plants produce sterols like beta-phytosterol as structural components of cell membranes, but evolution has loaded them with biological activity that turns out to be medically interesting. In this study, researchers screened multiple aloe vera compounds in silico, using molecular docking and molecular dynamics simulations, to see how they behaved in the presence of two key enzymes associated with Alzheimer's disease, acetylcholinesterase, or ACE, and butyrylcholinesterase, or BCHE. Both enzymes break down acetylcholine, the neurotransmitter whose depletion in the Alzheimer's brain leaves synapses quiet and memory faltering. Beta-phytosterol outperformed its botanical neighbors. It bound to ACE at -8.6 kilocalories per mole and to BCHE at -8.7 kilocalories per mole. Stronger affinities than other tested compounds, including succinic acid, another metabolite present in the plant. These results highlight the potential of beta-phytosterol as a dual inhibitor, which could be crucial in managing Alzheimer's disease, said lead author Miriam Kedrawi. There is something fitting about this discovery. Has been cultivated for over 6,000 years, appearing in Egyptian papyri, Greek pharmacopoeia, and Chinese herbal traditions, almost always in the context of healing. Modern phytochemistry has begun to decode the molecular reasons why. The plant's latex layer, just beneath the thick outer rind, contains anthraquinones with antimicrobial properties. The clear inner gel is rich in asamanin, a polysaccharide with immunomodulatory effects. And now, nestled among its sterols, beta-phytosterol appears to be doing something quite remarkable at the neurological level. The compound's stability was confirmed through molecular dynamics simulations, the computational equivalent of watching a molecule settle into its binding site and stay there over time. A compound that binds strongly but briefly is of limited use. One that binds and holds is far more promising for drug development. ADMET analysis, which models how a compound is absorbed, distributed through tissues, metabolized, excreted, and whether it may be toxic, returned favorable results for beta-phytosterol. This is perhaps unsurprising for a compound that plant-eating organisms, including humans, have consumed throughout evolutionary history. The comprehensive analysis supports the potential of these compounds as safe and effective therapeutic agents, noted co-author Samir Chetita. Succinic acid, another of its metabolites, also fared well in safety profiling, though it did not match beta-phytosterol's binding affinity for the target enzymes. The researchers are careful to note that computer simulations, however sophisticated, are not the same as laboratory experiments or clinical trials. The path from a promising phytosterol to an approved Alzheimer's treatment is long and demanding. But computational screening serves an invaluable function. It narrows the field, pointing researchers toward the most promising botanical candidates before expensive and time-consuming real-world testing begins. What offers, in this sense, is not just a compound, but a starting point, a natural scaffold, forged by millions of years of plant evolution, that human chemistry might refine and adapt. Our in silico approach offers a promising direction for the development of novel treatments for Alzheimer's disease, said Kadrawi. The desert succulent, it seems, has not yet finished surprising us. Thank you for watching. Stay healthy.